This video is being created to walk you through the 5 requirements for lab submissions. The following is an example. Please be aware that this example is used to demonstrate the lab requirements and not to provide a tutorial on how to solve the problem. For details on how to solve problems like this, refer to the information included in the first lab exercise. So our problem asks us to calculate the distance a spacecraft takes to get to the planet Vulcan. We're also given a formula that we will use to do the calculation. So we'll start with that formula. Time is equal to distance divided by velocity. Now this is going to be a multi-step problem, so I'm going to use multiple lines in my calculation. If you're comfortable with equations, feel free to use as many lines as you wish, even all in a single line. So to start, we know we need distance in the time calculation, so we write it down first. We can immediately see that the units in the problem don't match. Here we have light years, and our velocity is in meters per second. It's easy to convert light years to meters. The conversion factor is given to us in the problem statement. We'll do this as a separate step. We're given the distance conversion to be 1 light year is the equivalent of 9.46 times 10 to the 12th kilometers. Doing the conversion is going to look like this, with the like units canceling out, leaving behind kilometers as our result. Now we're going to solve the equation distance divided by velocity. So our distance translated down in the second line, 1.54 times 10 to the 14th kilometers. Now we're going to have to convert kilometers to meters, so we do our first step in the conversion. So here again, canceling like units. So now we apply the velocity. So here we're in meters per second. But we know that the answer is going to be in years, because that's given in the problem. This result leaves our answer in seconds, so we must continue to convert seconds to years. So as we go through, with each conversion factor canceling the next, until we are left with an answer in years. So we've arrived at the correct answer, and we've identified it with an underline. Now that we're done with the calculation, let's go back and look how we've satisfied the 5 lab requirements. First, we notice that we have an answer, a final answer, that is underlined. Our answer is in scientific notation. Our answer also includes units. We note that each step in the calculation, starting with the original formula, all of the math follows to the correct answer. We also note that we've shown all of the work that it takes to get from the problem statement to the result. Now let's look at some examples of what it looks like when we don't follow the requirements. Here, in this problem, we didn't use scientific notation. Now notice the standard notation numbers are very large. Why would we even want to do this when we can simplify our lives significantly by using scientific notation? Using standard notation with this many numbers and numbers that are this large are very prone to error. Make sure that you use scientific notation to save yourself not only a lot of trouble, but also the potential for error, each of which is going to cost you points in the course. Here's an example without units. Not using the correct unit is very easy if you don't show what the units are that you're using. It is also very easy to miss a step and applying incompatible units when you're doing equations with multiple steps. So how would you even know if you've missed a step or if your final answer is not in the correct unit as specified in the problem? Now, although the answer here is correct, you can see how easy it would be to forget a conversion factor. In our next example, here is one where we didn't show any work at all. We just simply wrote down the equation and came to an answer. In this course, a lot of our lab work is going to require multiple steps. Failure to show your work is an indicator that you didn't actually do the work and looked up the answer. In this class, getting to the answer is just as important as the answer itself. So you must demonstrate you know how to do that. In this example, You see the work being done, but the actual final answer is not being identified. Here you see that there are lots of interim answers. Failure to identify the answer by not identifying it is an indicator that you may not have known what the correct answer actually is. If you do the work, please identify what the final answer is. I'm not going to assume that the last calculation is the final answer, because many times student work does not flow linearly like that, as you can see in this example. This example is very similar to ones that I often get submitted. I won't assume that yours follows in a linear fashion either. Demonstrate that you know what the answer is. In this example, you see the calculations, but the math doesn't follow. Again, it is vital that you demonstrate that you know the answer when you get it. Remember that getting the answer is just as important as the answer itself. In this example, the student didn't bother to verify that the units all canceled. Therefore, because the conversion units are not there, the wrong answer was the result. If you would like additional examples of what the lab requirements look like, you can always reference any of the lab answer keys once they have been posted. Each of them will demonstrate the requirements where applicable.